Okay, hello everyone, and welcome to vJUG. I was about to say vJUG 24, not for a while, but vJUG. We have a session, event sourcing, distributed systems, and CQRS with, was it Java E? Maybe
with Java EE.
with Java EEE. Okay, and joining me here is Oleg Shalaev. How you doing, Oleg?
I'm doing pretty well.
And as you can see from our shirts, actually, we are at Geek Out, but not Geek Out Estonia. We're at Geek Out Boston. So we're doing this session live from the East Coast. Geek Out Boston was a half-day conference that literally just finished today. And joining us, whereabouts are you actually, Sebastian?
I'm based in Munich, Germany.
Okay, there we go. So joining us from Munich, Germany, is Sebastian Daschner. How are you doing, Sebastian?
I'm pretty good. And yourself?
Not
How's
too
Boston
bad.
going?
So, Boston's nice actually. It was like 34 degrees yesterday, and now it's dropped down to about 21, which is far nicer. So let me introduce you. This is your first time on the virtual jug, so welcome.
Yes, it is. Very first time.
Excellent. And you are a Java champion. You are a double Java 1 rockstar. And you are obviously heavy into Java EE. In fact, you are also on the expert group for JAX-RS and JSON-P. And your day-to-day role is as a developer, as a consultant, and as a trainer. So it's our pleasure to have you on board here. One thing we should probably announce just before we start, actually, is the report, Rebel Labs report. That if I point this at you, then you can talk about it.
Yeah, almost forgot about that. So at Rebel Labs, what we do, we run the surveys among Java developers, and we try to promote them as much as we can to reach as many developers as we can. And we ask questions about the tooling that you use, or some questions about your best practices or processes within the team. After that, we crunch all the data, analyze the responses, and try to produce a very comprehensive and interesting report about the state of the ecosystem and the community. So this year, last year, for example, if you want to check it out on Rebel Labs, you can see that we had a tools and technology report. I'll be sharing link if you need in the RC chat momentarily, but it was very interesting. So this year, we would like to know, why do you use certain tools, and what are the reasoning behind picking tools, and does that reasoning differ in different companies based on company size or the project type? And it's fairly short survey. You just can click through that in no time, and the more responses we get, the merrier the data will be. And I will be sending the link. I will tweet the link as well.
Why don't you email the vJUG list that?
I think I did that already.
You have done. In that case, everyone already knows about it. So I'm sure we've probably got an extra 11,000 signups probably just because of that.
Yeah, yeah. Didn't happen. So if you received that mail and you didn't act, I'm deeply disappointed by that. I will be sharing that link again. So if you have a moment, just take your time and share it with your friends as well, colleagues. That was the minute of Rebel Labs plug.
Awesome. And looks like we've got some good numbers here for this session. So without further ado then, Sebastian, I'll pass over to yourself there, and we can start the session.
Awesome. Yeah, then hi side from my as well. My name is Sebastian. So this is a buzzword-driven session about CQRS and event source systems and event-driven applications together with Java. So yeah, Simon already kindly introduced myself, so I'm doing a lot of Java. And yeah, let's just start with the topic CQRS. Why should we even care as developers, right? So the thing is, when you're doing enterprise applications, then you're probably doing something with CRUD, right? So you're building some kind of databases, you're building some create, read, update, delete models, as we have done that for roughly 1,000 years, right? So why do we need something like CQRS or event-driven applications? Let me start first with what is wrong with CRUD. First of all, there's nothing wrong with doing so, but you have a couple of shortcomings, especially when you tend to build bigger systems, right? So how do we do CRUD-based systems? We basically store the state of our system in a database, right? You have some models, you have DTOs, POJOs, objects, whatever. And all these objects have some state. And that current state is stored in the database. And once you change something, you have a new current state. And the old state is forgotten then. So first of all, one thing that comes into play, you totally lose all the history and the context, right? You can't know how the system got into this current state. And then also, since we want to be consistent, you have to deal with some, well, competing transactions, right? User A wants to change the state and user B wants to change the same state, and one wins and the other one loses, right? So you have to take care of that, and you have to basically synchronize this. And because of that fact, you will not be able to scale forever, right? So this is the problem due to CAP theorem. A CRUD-based system with consistency will never scale forever. And now about two motivations that I see as the main motivations behind CQRS, and I want to introduce them first, and then let's go to the topic later. Oh, and there will be a lot of code later on, but I think it makes sense to introduce the concepts first, since my experience is that most of developers are not that familiar with CQRS yet. So what are the motivations and why should we care? There is a model or approach that has been around for quite a while that is called event sourcing. What is an event source system as opposed to a CRUD-based system? We basically store everything as atomic events, so things that happened to our system. Rather than having the current state, we just store everything that happened in the atomic way. The best example is money transactions on your bank account, right? You have some deposits and withdrawals in your accounts. And if you want to have the current balance, well, you start from day 0 and apply plus, minus, and so on and so forth. And then you end up with your current state. But that current state is then calculated. It's not stored persistently, or not necessarily. The base of your system are these events. And these events are basically all the use cases that happen to your system. So if the user does something, create transaction, create user, or the article, that will be an event. And that event is stored in the system. And by doing so, you per se have the full history and the full context, whatever happened to your system available, which at first is quite a benefit, right? Because you can debug, you can backtrack later on everything that happened to your system. And this also, if you think about it, enables some kind of things like what I would call future use cases. So for example, if your manager comes 2 years after you started your project, and because manager do those kind of things, asks, by the way, how many users did sign up on a Monday to our system? And then, fair enough, as a developer, you can say, well, this was never specified, I have no clue. But in an event source system, you basically can answer that question, since you have all the user sign up events there, and you just later on calculate what happened with the timestamps and when these events happen, and then you can do all the statistics, even though you didn't know about that 2 years before. And this is also quite a benefit of this. However, to do event source systems, you don't have to be distributed, you don't have to care about CQRS. You can actually implement an event source system, and that has happened a lot with a relational database with a consistent way, and that's it, to get all these benefits here. But now about the second motivation behind CQRS, that are event-driven architectures. So why is that a thing? Well, if we have several systems involved, then, well, if they want to scale, you have to do something different than a CRUD-based way. So basically, if you involve several systems and you want to be consistent, that is probably a bad idea if you do something like distributed transactions, right? Because they simply do not scale. So distributed transactions mean you go to system 1, you lock it down, you wait, you go to system 2, and then at the end, you do a all or nothing transaction, but basically you have to lock everything down, and this will never scale. So in order to solve that, you have to split your transactions up into several ones and then communicate via events. And let's see how this works with an example, or what is the idea behind that. So let's go to the real world. Probably most developers try to avoid that, but if you think about the real world for a second, and let me put up this sentence. The real world is all about collaboration, hopefully good intentions, and then eventually dealing with issues or with errors. And what does that mean? So let me tell you a story. Imagine there is this guy, Sebastian, and he's hungry and he wants to go to a restaurant and order some burger, right? So what does he do? He goes to the restaurant, asks the waiter, can I have a burger, please? The waiter says, yes, sure, and accepts the order. So if you think of a consistent software system, then you may think now the order is in the system and it's fully consistent, and of course you will get your order later on. But actually it's not the case, because what really happens is that your waiter just accepted your order and then will later on go to the chef and actually gets told, sorry, we're out of burger in the restaurant. And then even though I was told, well, we have some burger, they may come back later on and tell us, actually, it's not the case, we're out of burger, sorry, even though I accepted your transaction, if you want, before. So it may also be the case that because I'm not the only guest in that restaurant, that another guest orders the same burger at the same time at a different waiter, and that's actually the last burger available, and then they can fight who wins, right? So what it actually happens then, the waiter will come back and tell us, oh, sorry, we're out of burger, but it's such a lovely day, how about a salad instead? And whether that's a good substitute or not, that's fully up to you. But this is how the real world works, right? So you have to deal with some errors anyway, because a lot of things may go wrong until you get the burger. The whole restaurant may burn down if you want, but you have to deal with some potential errors anyway. So if we build software systems, which are hopefully built for the real world anyway, we have to think of all these problems, because that restaurant is probably not consistent, right? Because otherwise, well, you have to lock down the whole restaurant if you want to order something. So this doesn't work. And this is what I mean. It's all about collaboration. And the intention there is, I had the intention, I want to order a burger, which is fine, and that order was accepted, and it may come later on, but it's not consistent. It's actually eventually consistent. And we have to deal with that error later on. And now about the event-driven architecture here. What that is and how these events work. Let me give you a second example. This time about coffee. So imagine we are at the coffee shop, and actually this example I will use later on for the code, how to implement this using Java and Java Enterprise. We're at the coffee shop, and we have several microservices involved here. So this is, of course, scalable. So the order system is a separate system, the bean system, and the barista. So the order system is available, there for handling orders with the clients, with the customers. The beans system stores the coffee beans. So imagine the orders have different beans, right? And you have to somehow arrange that. And the barista system is there for actually brewing your coffee. So now what happens, if you want to order a coffee here, you want to place an order, and let's say it has to be validated so that there are actually beans of the specific order coffee type are available, and so on and so forth. So what you could do, if I say order coffee, if we do it the traditional way, then we have to lock down the beans system, ask it, are these specific beans available? And only if that returns, then we can actually return the order and say, okay, it was accepted. And it will be possible since we validated it using the external system. However, that does not scale. If we have a database involved here, then we have some distributed transactions already, and this does not work. So what we do instead, we use events. And how this works now, we have the attention order coffee, and then order has been placed. We only place the order. This never means it will be possible or something like that, but it has been placed. We go to system A, that is now orders, place the order, order placed, and then the client returns. It's accepted now, come back later. Same like in a restaurant. I accepted the order. I will never say that it's possible or not. But now the order placed event, and this is an event, is in the system. And how this works now is that all the systems communicate via these events. So they can subscribe to these. For example, the bean system may be interested in that order placed because it knows that if an order has been placed, we have to validate it. And this is now the second intention, the command. We have to validate the beans. And then whether the bean system knows there are beans available or not, then another event happens. Either order beans validated or order failed due to insufficient beans or something like that. So what happens, we have commands and then events that happened or potentially errors. But all this big use case transaction gets split up into several transactions here. So the first one, that was one transaction, placed the order. Now it has been placed. The second transaction in the bean system will validate the beans and so on and so forth. And only once the beans have been validated successfully, then we say, now the order system listens to that event and can now process further on by saying, now we can accept it. And then this event order accepted happens. And that's how event-driven architectures work. So these events have to be published reliably. So what that means that we split up our transactions into several transactions, but they still have to be consistent. So the same is for the first command. Once we tell the system, please place an order, then this has to be done in a transactional way. Because when we go back with a successful response, then the client should know at least that this is in the system. It may be possible that it's rejected or possible later on, but it cannot disappear. It should be in the system. And yeah, this is basically the connection to the real world, since we need that collaboration sooner or later anyway. And by the way, you're trusting on outdated information in the real world also, right? If you imagine that restaurant example, and then the waiter telling us whether that burger is available or not, you have to deal with that. And this is one reason why you can build it in. And now going back to that example, then once the order has been accepted, then the third system will listen to that event and start the coffee, and then start the coffee brewing, and then the order will be updated, and so on and so forth. And what the client can do now, since the client returned at the very beginning, it can come back later and asks for the status here, so that these events will be used to update this. And later on, we can finish and deliver the coffee, and so on and so forth. And how this now is done and integrated with having a model to update with the client being able to read the status, now our buzzword CQRS comes into play. CQRS stands for Command Query Responsibility Segregation, for long words. If you put them together into one word, then it could be German. And it basically means we separate the write side from the read side. So that means we either have a write, like changing something in the system, or we reading from the system without changing anything, without having any side effect. In Java code, that would mean a void method, changing something, or a getter without having any side effect. So that means these commands, like these intentions that we have, these methods that are called produce events, or nothing happens, or an error is thrown, but nothing else. We are only communicating via these events. And the query reading something only returns data. And it will not throw any events, and it will be free from any side effects. And in order to get this working, as I said before, these events have to be handled reliably. So that's the important thing here. And then about how we build up such a CQRS system. So what that means when I say we split up the query side from the command side. So what we now have, we have a command service on the left side here, and we have a query service. And they only communicate via events that is sent over an event hub or event store. And each of these systems have their own representation. That could be a database, that could be in-memory storage, something like that. And all these systems individually could be replicated. So we could have several instances of this. And they are all independent. That's quite important later on. So they only communicate via events. So for example, if we go back to that coffee example, for our architecture now, that means we placed an order, right? We want to order the coffee as a client. So of course we go to the command service. Since the command service is there to write something, to change something in our system. So we place the order at the command service, and it may do some internal validation that is just be used from the representation in the command service system. And then it basically places an event, places an order, and publishes that event reliably to the event hub or event store. And that's it. Once this is published reliably, then the client returns, HTTP 202 accepted, fine, come back later. I can't tell you now if it's possible or not, but your order is in the system. And then what happens is the event hub publishes that event to all the consumers. For example, on the query side, the query service also has an internal representation of coffee orders, for example. And all the events are applied to the internal representation, and then the current status is calculated. And the current status is exactly that, what is stored right here in the in-memory representation in a database or whatever storage you have here. And once the client comes back later and wants to read that, it will return this representation from this storage. And all these services only have this, so they can subscribe to the events, and eventually some events will appear there, but they only can use their database. And so this is how that works. Once you change something in the command service, that will trigger new events, and all these events on the query side and on the command service side are used to update the internal representation. And also there will be some kind of event handler on the command side, of course, that will then process our request further on, right? Once there are some events that we are interested in, for example, that order has been accepted, then we can do something and trigger new commands that also will then publish new events that will be used to update all the internal representations. And now what we have using this CQRS approach, first of all, we can scale independently, since all the databases that are involved are just there for each and every instance. So there's no database sharing, since you actually also shouldn't do that in using microservices, right? Shared nothing architectures. We only communicate via these events. So we can scale independently as much instances as we like. Our event hub will update all the consumers. And all the sites, actually, since we are splitting up the read side from the write side, can also scale independently, which is quite interesting, since for most of the enterprise applications, if we look at the actual usage, you will see that normally the number of reads highly outperform the number of writes, right? In some web-based system, you will have a lot of reads, a lot of GET requests, and eventually you will have some writes, some changing something in the system. And now using CQRS, that means we can fire up, for example, a lot of read sites that all get updated once new events arrive, and they will use their internal cache or their internal database to then output this data with high performance. And also outputting this is quite fast, since you can do, for example, just in-memory caching, and nothing will change that state unless new events arrive. So that's the nice thing about these events. They're immutable and they happened in the past, so we can cache them. Oh, by the way, that also means event source systems, you cannot delete something, right? So if you want to delete a user, then, well, user deleted event will be there. And then if you calculate the current state after that user deleted event, then the user is gone. But all the information is always there. And that means if you build up some old state on these events, you don't have to throw anything away, because that's immutable. It will still be there, and you can optimize that quite well.
Quick question, Sebastian.
Yes.
From on IRC, from Kuba Ziguba. Why does the command service have access to the database on that previous example?
That's a good question. It doesn't actually have to have access. If you want to do some validation, for example, so if you're not just blindly accepting any commands and saying, fine, we will publish an event, then you need some internal representation to validate, for example. And that internal representation will also be updated once the events arrive. So actually the same thing like here happens there, or was in that picture. So once a new event arrives to the event store, then it will update all the consumers that are interested in. And this, of course, depends on your application. But if your command service also has an internal representation that is used for validation, then this is stored right here.
Perfect. Thank you.
Yeah. And yes, a nice benefit is you get read failover availability for the read side. So for example, if your event store or event hub breaks down, that is the equivalent of a CRUD-based system not having a database. In a CRUD-based way, you can at least read from all the instances that are available, right? So if this event store is not available, then still all the representations on the query side can read. You cannot store anything because that will publish an event, but the read side is still available, which is a nice benefit. And now let's go into code finally. So CQRS and how to implement this with Java and Apache Kafka, and why blue pill versus red pill. So if there are any questions anytime, then feel free to ask. So what I've done here, yes.
CK1. Oh, nice. CK1 spelled SCAKAY1. Anyway, are commands shared with the event store, or are they simply HTTP calls?
The command, well, it's whether it's HTTP or not, that depends on your application, but they are not really shared with the event store. So a command comes into a command service, and however that comes in, and then this command service does whatever and decides a new event has happened, and this will be published to the event store. But the event store doesn't know anything about, well, the HTTP site here or how actually the command looks like. It just sees an event has happened, and that is a fact, and the command service decides whether events happen or not.
Okay, thank you.
So what I have here, the example with the scalable coffee shop. So we have a coffee shop that is split up into these three systems that we just had in the example. And actually all that is on GitHub, available as code, scalable coffee shop. And what it is, these are Java EE applications, actually 3 of them, since we have 3 microservices if you want. And of course, I would love to live code all this from scratch for you, but I was told I only got 1 hour today, so that will probably take the whole day. And this is also a topic for later on, that implementing CQRS is far more overheads than just the simple CRUD-based way. But you will see that in a second. And also, the interesting thing here is I didn't split up the systems into a read system and a write system. Just for simplicity, I could do so. So you will see that all the logic is actually split up and separated. You could equally well have 6 systems or then 12 systems, or how much you like. But let's start with an overview of that. So if there are any questions, just feel free to ask. I have to show a lot of code that's prepared up front. I normally don't like this approach. I would love to live code for you, but otherwise it's not doable. So what we have HTTP communication here. We first of all want to order something, right? Order a coffee. So we have a resource, a CQRS resource for our orders. And now this resource, and here you see that we have, of course, a post and a get. So this is obviously a command, and this is a query. And then starting from that, it's all split up. So we later on have a command service and a query service. And what we're doing, of course, if we change something, if we have a command, then this would probably be a REST call HTTP post, right? We're posting something, we're posting a new order to our system. And this happens over JSON, and then a couple of things like UUID are generated, and basically the command service, because we're changing something, is called to place an order. And what it is, the command service, now, for example, we don't want to do any validation. We tell the event producer, I will show later on what that is, to publish a new event. Order placed. This is now a fact. This is an event that happened to a system. It can't be changed. It's immutable, and we publish that. And once you see this is void, once this returns without any exceptions, then it means we can be sure that this is in our system. And it will return and tell the user HTTP to accept it. Thanks, come back later. And in the same way, if the user comes back later using that ID and wants to get the status of the order, then it will use the query service to get the order back. And then it uses what in DDD world would be called an aggregate, or here it is a store. I will explain later why I'm using this approach. That basically contains the current state of the system here. So this is the equivalent of having a database. And now for simplicity to show that approach, I'm only using an in-memory storage here. So everything is stored in a concurrent hash map. The reason why I have this approach using a singleton is that I have one bean that is available as a singleton, so only one instance in our system that has the current status. Well, like a database, but in memory. And this actually implements all the changes that arrive from events. So you will see that the client uses this one to fire the queries to get something back. And how this is updated is done using @observe this CDI using CDI events. So Java EE already has some events available, natively built in using CDI events. So what we can do, I defined all these business events, and they will be thrown as CDI events once a new event arrives to a system. And this will then use the business logic to update all the status. So once, for example, a new order has been placed, then a new coffee order will be created and stored in our database. And on all the events that happened, they will be applied to our bean here. And this has some state here and some information. So this is basically our business object that will be stored there. And this will be returned once the client comes and wants to read the status. So now that's the easy side of that. So how the implementation using Apache Kafka is done is I'm using Apache Kafka since it's used quite a lot right now as a good example. And what we're doing, as I said, we're subscribing and publishing new events. And the connection to Java.EE is that once an event comes into a system, then it will be fired and triggered as CDI event. And that is done here in the so-called or the update consumer. So for all the systems, we have consumers that basically change something in our internal representation by firing CDI events. This happens here. And the connection to Kafka is this, well, I wrote an event consumer here that opens up, where is it, a Kafka consumer, and subscribe to these topics. And the reason why I'm doing this here, because it has to run, well, first of all, infinitely until it's shut down. And also it should integrate in the Java.EE environment well. And if you know about Java.EE containers, you should not start threads yourself, and so on and so forth. So this is the reason why I'm using a managed executor service to start this as, well, a new event consumer that will just run until it's gracefully shut down. And actually this shutdown happens once the application server shuts down. So the add pre-destroy annotated method in Java.EE will then gracefully close the consumer, and it will stop. And what it does using a Java 8 consumer here, it basically accepts this value, our event, and this event will then be fired in CDI. So this is the integration that is, other than that, transparent to the application. The application can just subscribe to these events as shown here, and then they will arrive in the system once they happen. On the event producer side, it's also quite straightforward. On the Kafka integration, we have a producer that goes to some topic and then fires that event. And also, once something changes in our system, so if we, for example, have these events that have to be processed, then we have some kind of event handler that then triggers new commands. Because the updating side is only be used in the query side, right? Or it could also be used in the command side, but the thing is, the query side will not trigger new events. So the query side will only be updated using these events, but the command side has to have an event handler. And that event handler does a similar thing. It's subscribed in this case to other topics. I have a topic defined for each and every system, for the beans, barista, and the orders system. And for example, the orders system is interested in the two other topics to consume, to fire new potential commands. And this happens here. So this is then actually the logic that triggers subsequent commands, for example, to cancel an order, to accept order, and so on and so forth. And this is as if the user would trigger it from the outside using HTTP. So this then triggers, show this in, this is basically that side that calls a new command on the command service side. And this may, well, for example, cancel an order and trigger new events then. And these events are then published as well. And this is how the workflow works here. And the reason I've done this in 3 applications is, so now we have 3 services, microservices, and also we have then 3 applications and, well, 3 running application servers. So how I'm building this is that I have the Java.EE 7 API, and the nice story about that, we can integrate this into Docker base images, and then we have a really lightweight build solution. So that means our 3 WAR files only contain our business logic. And the Java.EE API, and if we want also the Kafka API, is then included in some base image. So what I'm doing, of course, I'm using Docker to run all this. So I have some Docker files using, well, a private base image. And the base image already includes everything we need for the implementation side. So, of course, operating system, Java, application server, and in our case, also the Kafka API. So we have the application server already configured, and we just have to add our, well, thin WAV files there. And this is true for all the three systems. So the order system is probably the most interesting one here. What the other two systems are doing, the bean system is a bean storage, basically. So a similar thing, you have to store beans there, and then once a coffee gets brewed, then the beans get subtracted again there. And the barista system is basically a timer that then decides at some point that our coffee has been finished. So to run this example, I now have 3 command line windows open for our 3 systems. So they are all in one project, but they are totally independent and independent WAV files, and also independent Docker containers. So what we're doing here, we are building everything using Maven, and then, of course, building into the Docker image, and then just run this image using here the order system. So we built this using Maven clean package. Then it will build, even on that slow 6-year-old computer, quite fast, since we're only using the thin Java EE API, which is provided. And here you see the application server is already starting up, and then it connects to Kafka. And the same is true for the other 2 systems. So now this was the order system, independent, only connecting to Kafka and consuming. The second one is the bean system, and the third one is the barista system here. So what it does, it's, well, not that fast. This one starts up the other application servers as well, and then we have the 3 application servers up and running. And now we can use, for example, the command line to connect to our systems using HTTP. So we say, for example, localhost port 8001 is the order system. Context orders resources orders. And then, of course, method not allowed, because you're only allowed to post something there or use the ID to get to read an order. So what we can do, we can now post, for example, a new coffee using this JSON approach to our order system. And then what happens? To accept it, right? Order has been placed, fine, come back later. And we have our ID. And now, actually, if you look at the system and if you look at the output, then you will see, oh, something happened, and at the end, order canceled. Why is it canceled? You will see it in the log here, beans not available. So actually what happens, you have to have beans stored in your bean system before you can brew some coffee. So the order has been placed. This is noticed in the bean system, and then some order placed here, and then it's validated, and it actually says order failed because beans are not available. And then immediately the order has been canceled. So once we come back later now and ask our system, that's the wrong link, what about our link, what about our coffee order, and go to that provided ID, then it will say, oh, actually, status canceled from our espresso because beans from Ethiopia, for example, are not available. So even though, and this is exactly this being eventually consistent, even though it was accepted in the first place, this only means that the order has been placed, right? And it's not possible. And so it will immediately be canceled. But in an asynchronous approach, the client returned first. So what we can do now, we ask the bean system, give us some beans, and you will have an empty JSON response, so there are actually no beans available. And this means we have to post some new beans to the bean system. Port 2. with that JSON, we have some, well, bean origin now Ethiopia, and we want to add, well, an amount of 10 new beans. 2 for no content, fine. And then some beans will be in the system. And you will see, well, beans stored. This is also an event, of course. So now if we do the same thing and actually order some coffee. Oh, sorry, this was the wrong event. Now we have some more beans. We want to order some coffee. Then the same story again, 202 accepted as before. But now you will see that actually a couple of things happen. Order placed first, and then the beans are valid because now we have some beans, and then the whole process order accepted, and then the barista system comes in and says, now I can start my order because I'm only interested in accepted orders. I start my coffee brewing, and then eventually the coffee brew is finished. This is a timer. So if we come back now and ask for the status, well, it's already delivered. I was too slow. Finished, and then afterwards it's delivered. And as you see, once you keep asking for the status, then it eventually will be updated once these events arrive. And now that's done. That's the final state. We have a delivered coffee in that system. So let's do this again. We order some coffee here, 2 accepted. We can ask for the status. Now it's finished, and after it has been finished, it at some point will be delivered. So let's say we want to check here. It's randomly using some timer checks for unfinished and undelivered coffees, and then this order delivered event happens here, and the internal state is updated. And now about the implementation, a little bit more here. So what happens, as I said, everything is stored in memory here, which is easy way to integrate that, but of course it's not persistent. What is persistent are the events. And in an event store system, this is the golden source of truth. So this is the important thing, right? But of course, if we now go and let's say we kill the first system, so now it's gone, and well, everything in memory is not available anymore. And then we redeploy it, we start it up. What happens is that we can ask Kafka, please deliver us all the events that have been there from day one. And now all the events are then reapplied and used to update the internal representation. So once this system is up again, then you will see all the events here, order placed, order canceled, everything that happened from the beginning are redelivered and used, of course, to update the internal representation. And also, if we go back and ask for the same, random UUID that has been generated in memory before, it's still there. All the information is there because it comes from the immutable events that are delivered by Kafka. Of course, if you're in a production system, then you probably don't want to have this in memory, but also persistent, because what happens over time, your system gets slower if you do so, right? You have a couple of events now, then if you come back later and do this thing after 1 year, then you have millions of events, and on startup time, it's quite slow because on application startup, it has to apply all these events. So what you would do is you would, at this point, introduce a database, right? So that you have a persistent storage of your current representation, of your current state, quite similar to a CRUD-based system. But here you use that current state to, be safe against slow redeployments. And what you can do, you can actually do so because these events are immutable, so they can change. You just have to keep track of the offset that you had last. So which event was the last one I got? And starting from that, these will be delivered. Every event that was there while your application was down then they will be redelivered. Actually, Kafka does so in a reliable way. And then you can commit to the new state and say, this is now in our database. And now for more live coding, what we actually could do is that we implement some state here using JPA, for example, and then this coffee order would be persistent in a database, right? So, but instead of doing something reasonable, let's do something fun. Because what you could do, as I said, you can implement later use cases. So for example, if we would change some code here, redeploy our application, all the events get redelivered, and then, well, get thrown through your code as if all that state, as if everything would have been there since day one, right? So if you do some fix, if you add some features, then at the end you replay everything, and then your status will be as if that all these features have been there since day one. And I will show you this. So for example, let's implement some statistics here, right? So let's say we have our coffee orders, and let's keep track of all the delivery times. So how long does it take to place an order until it's finally delivered by our barista? And in order to do so, let's, for example, keep track of the order ID. And so what we have to do, the event comes in, order placed, for example, that means order has been placed, and we want to see how long it takes from order placed to finally order delivered. So we have to store this order placed for the order ID, and this order ID is a UUID, and we store that UUID for the current instant in time, that is the, well, point in time when the order has been placed. Orders placed, and this will be a concurrent hash map as well. And now we say, for example, on placed orders, order placed, put the get order info, the order ID with the event instance of when the event happened. And we store this here. So now in the future, on every placed order, we store in this map when it has been placed. And then at the same time, in order delivery, we ordered delivered, we can say order placed, give us the order ID, and this will be the instant in time when it has been placed, and then calculate was it until? Yes. Calculate from, now I have to think, instant, no, sorry, not now, from the event, that may vary, to from the beginning to the end in seconds. And this will be the number of seconds from the start when it has been placed to when it has been delivered, right? And now let's include another bean that stores our statistics. Let's say orders statistics, something like that. And this actually is used to gather all this. For example, we use this order statistic to save. Or order statistics, add a new statistic for our number of seconds for a new finished order here. And then at the end, it will give us the average of the current average of all the orders, right? So what it does here, it will store we'll store a sum and a count, right? And this will, sorry. This will add up the seconds to the sum, and it will increase the count, right? And on the average, we return, well, if counts equals 0, then we will return 0. Otherwise, we get a nice arithmetic exception. And then, I'm bad with maths, we have to calculate the sum to the count, right? And well, in order to be thread safe, if we want to do this as a CDI bean, we have to manage our own thread safety, read write lock. Let's add a lock here, and then of course this will be a write lock, right? Unlock, and the same story for there. Read write lock, read lock lock, and try catch, or try finally, read write lock, read lock unlock. And now we have the average in seconds here. Of course, you can use nicer types, but for now you get the story. And once we add this, then it's in our statistics here. And of course, in the same way as we can read the status from a coffee order, we can also output the average brewing time. That returns the order statistics, average. And this, of course, then can be accessed from the query service, right? So in the same way, you can say, give me the average brewing time by asking, well, my store, in this case, in-memory store that stores that in our new version. And of course, also, I can return this now in my REST interface. Let's call this statistics for now. Statistics, just to be faster now, query service, since I don't want to run over time too much. Average brewing time in seconds. And now this is there in our code. Now we changed something, right? And once we change something, we have to, well, rebuild it. So of course we have to redeploy it. Actually, we don't have to redeploy everything, but just the order system, right? Everything else didn't change. And what now happens, we rebuild our WAR file that also rebuilds then the Docker image, and then we start that up. And now, as I said, all the events will be reapplied. So that means all this status is now calculated on the fly. And for all these events here that happened, this is still there, that happened in the past, we can actually now say, give us some statistics. And for these two, I think, orders that we calculated way back in, that we placed way back in the past, this is now then be calculated as if that information was there from day one, because everything here happened in the past, right? But still, it's doable since all these events are reapplied. And that is a nice story about this. So you can redeploy that. Also, you could fire up a new, let's do this. Shop orders. Let's fire up another orders instance using a different port now. And the same story as before. We have now, well, duplicated our order instances, and it will also, well, connect and consume from Kafka. And we can ask the same things that we ask the first system also, of course, to the new system that never saw any of these orders. These have been placed by the first system, but it doesn't matter because we're just communicating over events. And now, Simon, how much time do we have left? I think we're short on time, right? Are you in mute? Okay, maybe Simon fell asleep. So let's just continue. Now about the...
Sorry, Sebastian, can you hear me now?
Yes, we can.
Do you hear a terrible echo?
Yes, I do. Should I mute myself shortly? So I think I'm the source of the echo.
No.
Okay, anyway, let me do two.
Hey,
I take that.
No, it's a terrible echo. Can you just crush it?
Okay, I will then now continue since nobody can stop me. Now about the blue pill versus red pill. So this was now all fun and games, but yeah, about the interesting things now, and well, lessons learned basically. So what is very important on this approach, that all these events are handled reliably. That means something that will be published in your event store has to be handled and has to be there in a reliable way. And this is what I meant by the split up transactions. So there are indeed still transactions available, but they are just there for, well, split up for a short amount of time, but they have to be reliable. And this is where it comes interesting, whichever technology you choose. So I choose Apache Kafka here. And well, now about the blue pill versus red pill. So if you're fine with the blue pill, then you can stop watching. But the thing about Apache Kafka, if you read into it, it doesn't guarantee exactly once semantic out of the box. What is that? Exactly once is how messages are delivered. And this is what you want. You want to deliver a message, for example, order placed exactly once. And what it does out of the box, if you use this approach that I did here, event consumer, if you commit something here, then it, well, waits for that commit, and this is fine. But if that system, since it doesn't do distributed transactions, breaks down in that very moment, then actually Kafka will re-deliver some events that already are known to the system. So this is this is meant with at least once semantic. And this basically, first of all, means that you have to implement idempotency on the consumer side. So basically, you can see the events by the event IDs, by the UUIDs, for example, and then see whether that event has been as known to the system or not. Or you can go more into details with Kafka now in this example and store all the offsets. So using the Kafka API, you can easily access the offset of some record. Actually, it's here in the consumer record, and you will see the offset there, and then keep track of that. But, well, this actually has to happen for a topic partition pair. And more about Kafka and how I'm using it. So the reason why this is redistributed, and the reason why all the events that are there for consumption are redistributed and not the event handler events. So this means why we, at the end, if we redeploy 3 times, we only have 1 coffee order and not 3, since the events are redelivered, right? It is because Kafka uses so-called consumer groups. And what it does, basically, you have a consumer group and you have a reliable message delivery per consumer group. And so what we want to do here, that each and every system has its own consumer group for updating, for reading the consumption to update the internal representation. And you have one consumer group for the event handler, well, per topic or per interested thing. So for example, one for the orders event handler system. And this has to be done in a reliable way. So that means that event create a new order will only be handled on the command server side once, and all the others are there many times. And if you think about this more and the semantics, then well, what I want to show here, or why am I saying this, is that you have to keep track and be aware of that problem once you build that solution, because it's very important, whichever technology you choose, that these events are handled reliably, and this means exactly once. And you have to keep track of that, especially with this event handler, because these event handlers must call these commands only once, of course, and that has to be ensured. And you can do this in several ways. If you look further into that topic in Kafka, for example, you store the offsets and then just reapply what is new, and so on and so forth, or you use another approach and store some offsets persistently in a database, or using, I used Apache Kafka as, well, combination plus the representation that it is an event store. You could also use, for example, a homegrown solution for event stores. That actually happens quite often. So for example, you can use a traditional relational database to build an events table and then keep track of what is published or not. But this definitely a further topic. So one last sentence about CQRS in general. Do you have to do CQRS in all these event sourcing approach? No, of course not, and also you shouldn't. About back to the beginning, the problems with or the shortcomings with CRUD. If you don't have to scale infinitely, and if you're fine with a CRUD-based solution, then perfect. Because as you saw in the code base, this is quite a lot of code, a lot more than you would have to do if you would do this in a CRUD-based way, right? So if you, same for microservices, right? If you can avoid them, then please do so. Then that's good. You can be happy and fine. End of story. Also, if you want to have the benefits of event source systems, you can totally implement them using a traditional relational database, using a consistent way of storing it in a database without, well, scaling forever. If you should do performance tests on your system, if your system is fully sufficient for that, that is fine. Then you have a consistent system. You don't have to deal with all these event-driven approaches. You don't have to deal with eventual consistency. Then this is great. However, CQRS is an interesting approach if you have several systems for any reason whatsoever, and if you want to do this event-driven way. And this is all I have for now. So thanks a lot for your attention. And if there are any questions, Simon, then yeah, please do so. So I don't know if I can't hear you. I don't know if it's possible with that microphone.
Hello, can you hear me?
Mm-hmm.
Just mute yourself.
Yes, I can. And it's fine. I can without too much.
Thanks, Sebastian. That was a really interesting session. Unfortunately, as someone was trying to say multiple times, but his microphone doesn't work because he was hooked to all kinds of hardware. We are out of time. We're going to be kicked out of this room any minute. So there is
good that I didn't hear it.
No time for questions. There are a couple of questions, I think, in the RC chat, and there was a live discussion there. We are trying to point all those people from the RC chat towards your Twitter. So if you could just be alert there for some time now for the questions, and I'm sure the questions will be coming later as well. So that's going to be good. Do you want to say something?
No.
Simon,
I think you pretty much said it all.
Yeah, Simon says that he's okay.
Of course, I want to say thank you to Sebastian for an awesome session.
Yeah, thanks for having me. Actually, when it comes to question, I can point
thank
to
you very much. And
sorry.
Yeah, to everyone else on the virtual jug, we have another session coming up in not too long. Unfortunately, my laptop's like super slow right now, so I'm not going to bother trying. But meetup.com/virtual jug.
Great. And just the last thing, I can point to that video course if there are any questions. So that is available for free. Want to have a look at that. So for the attendees that have questions.
Excellent. If you can just tweet that link at us, we would be happy to share it further.
Yeah, sure.
And
I will tweet that at
as
the
well.
GitHub project.
Excellent. Great. Thanks a lot. Thanks again, Sebastian. It was great.
Yeah,
everyone else, we're gonna see you at the next meetup. Check out how cool his setup is. Like that's the most professional vJUG speaker setup we had to date.
Okay.
And we've seen some impressive microphones hanging from the corner of the webcam view, but this is the best.
Well,
okay, Sebastian, once again, thank you. We're gonna go. Gonna run from this room.
Sorry for with the time I didn't hear your stop. So